Dear students, welcome back to this educational channel for chemistry learners. Today, I take you over to my presentation on spectroscopic principle and types. Today, I am going to explain the basic principle, terminology, and a different region of the spectrum used in various types of spectroscopic techniques. Hope it will useful to understand the basic concepts of spectroscopy that will be laid foundation for the forthcoming videos presentation on spectroscopy. Okay, now we go to the session. The first, what is spectroscopy? It is a study of interaction of electromagnetic radiation and matter to identify or quantify elements, atoms, molecules, molecular structure by observing absorption, emission or scattering interactions. Then what is electromagnetic radiations? So it is very important in the spectroscopic technique. The electromagnetic radiations are in the form of wave having oscillating electric and magnetic fields. If the electromagnetic radiations travel in z directions, then the electric and magnetic components are perpendicular to each other and perpendicular to the direction of the electromagnetic radiation. There are many forms of radiation starting from higher energetic, fast and narrow gamma radiation and to the low energetic, slow and broad radio waves. So actually this electromagnetic radiation has many different regions. So there is known as the regions of the spectrum starting from higher energetic gamma radiation to the lower energetic radio waves, and still more very highest radiation is the cosmic rays, but actually that is not our concern, because of we are only concerned with this gamma radiation, the regions gamma radiation to the radio waves only. So we are concerned only with this for our the chemical structural elucidation or other chemical applications. The next is, what are the basic terminologies of spectroscopy? So we used very different definitions, terms we are using in the spectroscopic techniques. Actually, the electromagnetic radiations consist of energy packets called photons, which travel with velocity of light. The different forms of radiations have different energies. In order for absorption to occur, the energy of the radiation must match the energy difference between the quantized energy levels that correspond to different states of the molecules. So the very basic requirement for absorption to be taking place by the molecule, if it is subjected to the electromagnetic radiations, the energy of the electromagnetic radiations and the energy difference between the different energy levels of the molecule should be equivalent or matching, then only the absorption will be taking place. Otherwise it will not be absorption taking place, no absorption will be taking place. So this very basic condition for the absorption to take place, and then only you will get the spectra, otherwise the spectra will not be obtained. And the terminology, the first term is the energy of the electromagnetic radiations. You see, the energy difference between any of the two states is represented by delta E. So the delta E is equal to h nu. The energy difference between the lower energy level and the high energy level is given by delta E. That's equal to h nu. H is a Planck's constant and nu is the frequency of the electromagnetic radiations. And wavelength, the second one is a wavelength. Wavelength is defined as the distance between successive crests or successive troughs of the wave. That we see now. Actually, it's a wave. You see that successive crest, that distance is known as a wavelength, or successive trough, that distance is known as a wavelength lambda. And next one is frequency. What is a frequency? The frequency is given. The unit is a hertz, cycles per second in hertz. Actually, it can be defined as the number of waves passing through a point per second. For example, you take any point through which the electromagnetic radiation is passing through this point. Number of waves passing through this point per second, that number is a frequency of the electromagnetic radiations. And the next one is a wave number. What is the definition for the wave number? Actually, it's the inverse of wavelength in per centimeter. It can be defined as a number of waves per unit distance or per centimeter. For example, per centimeter, how many waves are present in this 1 centimeter. So that number is given as a wave number. Actually, another way we can take it as a inverse of wavelength, that is in per centimeter. The next is, if the energy difference between lower and higher energy state is represented by delta E, the energy of the radiation necessary for matching is given by the equation delta E is equal to h nu. That can be represented as hc by lambda, because nu is c by lambda, where c is the velocity of light and lambda is the wavelength, nu is the frequency. Again, it can be represented as delta E is equal to hc nu bar, as nu bar is the inverse of lambda, that is 1 by lambda. So where this expression h is a Planck's constant, that is equal to 6.623 into 10 power minus 27 erg second per molecule. Nu is the frequency of the radiation. C is the velocity of light, is given as 3 into 10 power 10 centimeter per second. And lambda is the wavelength. Nu is the wave number. So the radiations can be characterized by wavelength lambda, its frequency nu, and wave number nu bar. Now we see lambda. So the electromagnetic radiations can be represented in lambda, that is the wavelength. That is lambda is equal to hc by delta E, the Planck's constant, velocity of light, by difference in the energy levels. And the electromagnetic radiations can also be represented by the frequency, the nu, that is equivalent to c by lambda. Then the electromagnetic radiations can also be represented by nu bar, that is a wave number, that is the inverse of the wavelength, that is 1 by lambda. Now we see the regions of the spectrum and interactions of electromagnetic radiations. So the regions of the spectrum means it's starting from cosmic rays and gamma radiations, they are the higher energy radiations, up to the radio waves. Different regions of the spectrum are there, and it will interact with the matter differently. So different data can be obtained by these interactions. So now we see what are the different regions and what type of interactions are there, that we have to see now. Now use this, see this table. There is energy is given in the kilocalorie per mole or electron volt, and wave number is given is per centimeter, and wavelength is given in per centimeter, and frequency is given in hertz. Now you see there are different types. The first is starting from the gamma rays, the gamma ray emission. Actually it's the nuclear transitions, and it's a very higher energy. You see this wavelength is somewhat 3 into 10 power minus 11 per centimeter. The energy is very higher. There is a 9.4 into 10 power 7 kilocalorie per mole, and this gamma radiations is a nuclear transitions. And the next lower energy is the X-ray absorption emission, and actually it gives the electronic transitions, inner electronic shell. It is a core electron, that is the electrons present in the core orbital, that can be excited by using this X-ray. And this energy is 9.4 into 10 power 3, and wavelength the range of 3 into 10 power minus 7, and frequency is 10 power 17. And the next one is UV radiations. There is a UV. UV is actually, there are two radiations. One is a UV, ultraviolet, and visible. Both are excite the valence electrons. Valence electrons can be excited, and it will be very useful to find out the nature of the valence electrons, that is bonding electrons or anti-bonding electrons or non-bonding electrons. That detail can be obtained by this UV absorption technique, spectral technique. And you see this the frequency is still lower. There is a 10 power 15, and wavelength is somewhat higher. There is a 3.3 there is a 3 into 10 power minus 5. And next the regions of the spectrum is infrared radiations. It is a molecular vibrations, the vibration spectroscopy. That is the energy is 9.4 into 10 power minus 1, and wavelength is 3 into 10 power minus 3, and frequency is 10 power 13. And it is very useful to determine the functional groups present in the different compounds. And the next lower region is the microwave regions. That is that's the energy is 9.4 into 10 power minus 3, and the wavelength is 3 into 10 power minus 1, and the frequency is 10 power 11 hertz. And this microwave region is very useful in that is study of the free radical and free radicals, and also in the ESR, the electron spin resonance spectroscopy. This region is very useful to know about the unpaired electrons system, the molecule. The last one is the nuclear magnetic, I mean the radio waves. It is actually, it gives It is very useful in the nuclear magnetic resonance spectroscopy. It is NMR spectroscopy. It's a very lowest form of electromagnetic radiation. Its energy only in 9.4 in 10 power minus 7, and wavelength is very longer, 3 into 10 power 3 centimeter, and the frequency is lower. There is a 10 power 7. So it is actually it is a magnetically induced spin state. It is a magnetic and electron interaction, electron spin and magnetic electron spin interactions both are involved in the NMR. So this is about the regions of the spectrum and the interactions of the electromagnetic radiations. The next, what are the types of interactions of electromagnetic radiations with matter? Now we have to see one by one. The first one is absorption. So the absorption, the radiation is absorbed and transmitted. So most probably the molecular spectroscopy is the absorption spectroscopy, and the next one is the emission. The light is given out, for example, by flame or spark. These emissions, atomic emissions by AES, atomic emission spectroscopy is one of the special spectral technique which is based on this emission of electromagnetic radiations. The next one is the scattering. The scattering of electromagnetic radiation, the path of the light is different due to scattering and the frequency also being different. So this scattering is very useful in the there is a Raman spectroscopy. The Raman spectroscopy is based on the scattering. The next one is what is spectrum. So now what is spectrum? It is a graphical representation of what is happened after electromagnetic radiations interacted with matter. Example, spectropropanone. The infrared spectrum for the propanone is given here. You see this is a spectrum. So the propanone actually it is interacted by the infrared electromagnetic radiations. Now the spectrum is obtained and it is shown in this figure. And now this is a spectrum. So the spectrum is the what happened after the interaction, that is electromagnetic radiations with matter, that will be given as a result. That is a result is given as a spectrum. Next, now we have to discuss on various types of spectral techniques using different regions of the spectrum, because already we have seen different regions of the spectrum. Now the different regions will use different technique, spectral techniques. Now we have to see one by one. So first the highest radiation, that is the highest radiation is a gamma radiation. Highest energetic radiation is a gamma radiation. Actually this is useful in the mass bias spectroscopy. So what is the principle of mass bias spectroscopy? Now you see the gamma radiation is higher energetic and narrow radiation used in mass bias spectroscopy. This technique based on change in nuclear energy levels leads to three types of interactions such as the electric monopole, electric quadrupole and magnetic dipole interactions. This technique is very useful to interpret the change in symmetry of the molecular structures. By using this technique we can see the symmetry, the change in symmetry of the molecular structures. So it's very useful technology at spectrochemical techniques and known as a mass bias spectroscopy. It uses gamma radiation. The next one is X-ray radiation is used in crystallographic studies, the crystal structure interpretations. Now how it is used, now you see here. To study about the internal lattice structure of the crystal or solid substance, the X-ray radiation is used, and the technique is known as X-ray diffraction technique, XRD. This technique is also useful to know about the unit cell dimensions, bond lengths, bond angles, and the details of lattice site ordering. So this is very useful in crystallographic studies, and here the X-ray radiation is very useful. The next one is electronic spectroscopy. That is electronic spectroscopy. The radiation used here is ultraviolet and visible radiations. This is also known as UV visible spectroscopy, and absorption takes place in UV visible regions. It is based on electronic transitions to higher energy level. The key parameters are, actually this spectroscopy is very useful in molecular structural interpretation. The key parameters are molar absorptivity, extinction coefficient, maximum absorption is lambda max. It is used in the organic spectroscopy, absorption. So these are all the key parameters. The next one is vibrational spectroscopy. There is the infrared radiations. This technique is based on the absorption of infrared radiation due to molecular bond vibrations. This technique is very useful to identify the functional groups in molecular structure. The key parameters are band location, band shape, band strength, wave numbers, transmittance. So the vibrational spectroscopy is one of the very useful spectral techniques it is very useful to identify the functional groups. Example, the hydroxyl group or amino group or a carboxyl group or many different functional groups can be identified by using these uh, spectral techniques. The next one is the rotational spectroscopy. Here the microwave radiation is used. The regions, the microwave regions is very useful here. The rotational spectroscopy actually is based on the rotation of the molecules in three coordinated axes, which differ in rotational energy, give rise to different moments of inertia, by which the shapes of the molecules can be classified. This is also very useful technology, and it is also useful in the next one is a electron spin resonance spectroscopy. Here also the same microwave region is also used, and sometimes the far infrared spectrum region is also being used here. Here this is known as the ESR spectroscopy. There is a electron spin resonance spectroscopy. This technique is based on the absorption of the substances with one or more unpaired electrons in microwave regions. The ESR spectroscopy is also called electron parametric resonance (EPR) spectroscopy or electron magnetic resonance spectroscopy. This spectroscopy is very useful in studies on free radicals and reaction velocities and mechanism, etc. Then the last one is the nuclear magnetic resonance spectroscopy radio wave region. Here we use the radio waves. This technique is based on the absorption in radio wave region in presence of strong magnetic field. It is used to determine the chemical environment of the molecules to interpret the molecular structure. The magnetically active of the type hydrogen, carbon, fluorine, phosphorus, nitrogen are useful in this technique. The key parameters are chemical shift, delta or tau, frequency, ppm or hertz, coupling constant, integral. So these are all the key parameters used in the nuclear magnetic resonance spectroscopy. This nuclear magnetic resonance spectroscopy is very useful in MRI scan in medical applications. The MRI scan, everybody knows this, and here they are based. Actually, this MRI scan is based on this NMR technique, the nuclear magnetic resonance technique. So this technique is also very useful in chemical interpretation, chemical structural interpretation, and also medical applications. In this last slide, we see some useful spectral libraries and software. So many libraries are available, or many softwares are available for the spectral studies. The first one is a SDBS. This is an Integrated Spectral Database, and ACT Lab, NIST Web Book, BioRads, Know It All and Have It All. Sigma Aldrich, there is a Sigma Aldrich is a very bigger chemical company. This also giving some information about the spectral techniques, spectral data of the very known compounds. And the last one is a Wiley chemical concept, spec info. So these are all very useful spectral libraries and software. So we can use these spectral libraries and software for your spectral understanding of spectral techniques. And so that's all about this spectroscopic types and principles. Hope this will be very useful for this, for your spectroscopic, the understanding of spectroscopic techniques. And the next presentation we'll see about the electronic spectroscopy of the coordination complex, especially term symbol and term states. That is going to be my presentation on the next presentation. So until then, thank you for your watching.